Okay, well now we're ready to take our measurement. So we've set up the spectrometer so that it's operating at the highest resolution, and we told it to start acquiring data. It asked us for a file name, and now we're ready to go. All right, and it's off. Now, here's where you're lucky to be doing the experiment remote. Taking the data that we want at the high resolution that we are asking for takes about 15 minutes per file. But we don't have to wait. We can just pause our recording now and then skip to the end. So let's do that. All done. Take a look at the data that you see now. You can see several series of bands across the spectrum. Okay? It looks somewhat similar to what we looked at in the low resolution preview, but this is much higher resolution. Starting from low frequencies, first we come to a rather sharp, narrow band here, then to some relatively weak lines that are broadly distributed, then a series of lines here, a second series of lines here, and then at higher frequencies, some more weak lines. Actually, by their positions, we can identify these things. These features here and these features are transitions associated with water vapor. If we removed all the water vapor from our file, these would disappear. This feature here is due to carbon dioxide, and we'll investigate it more carefully in the future. In addition, this is associated with carbon dioxide too. These are all row vibrational lines. They're transitions in which both the rotational and vibrational quantum number change. In this case, where the vibrational mode is the asymmetric stretching mode. In this case, it's a bending mode. Something interesting about the set of lines at low frequency, at about 600 wave numbers, although we're not going to investigate these further today, they are important. The reason that they're important is that these lines, these absorption lines, occur at the point in the spectrum which is about equal to the peak of the black body spectrum of an object at 300 degrees. That means these are well suited to absorb thermal radiation from the Earth. And in fact, it's this band of modes, of lines here, that are responsible for the effect of carbon dioxide in contributing to global warming. Finally, the main thing that we're interested in right now is this set of lines here, which are due to carbon monoxide. Here, we can zoom in on them for a second so you can see them more clearly. There, whoops. Here they are. These two sets of lines, absorption lines, very strong, very narrow, are due to carbon monoxide. And that's what we'll investigate further. Now, in order to complete these measurements, we need to take a second measurement. This is a sample measurement, but we'd also like to get a reference measurement so that we can subtract out or ratio out any features that aren't due to the gas in the cell. That is, any features that are due to the cell itself or due to properties of the spectrometer or the source or anything else. The way that we'll do that is we'll take a second spectrum, which we'll call the reference spectrum, and that'll be a transmission spectrum of an empty or evacuated cell. Here, 1 second. Here's our cell, which is currently filled to 1/2 an atmosphere with our carbon monoxide mixture. And so what we're going to do now is to seal the cell from the carbon monoxide and open it to the vacuum pump. And very rapidly, the pump will remove all of the gas from the cell. Okay? If we take a spectrum now, we'll just see absorption lines or other features associated with the cell itself with the spectrometer, but not with the gas. Okay, now we've taken our reference spectrum of the gas cell, and you can see what this looks like. The absorption lines due to carbon monoxide are gone. The water vapor lines are also pretty much gone, meaning that most of the water vapor in the spectrum before actually was carried along with the carbon monoxide into the cell. There's still a relatively strong signal from carbon dioxide, meaning that this is not so much due to the gas in the cell as it is due to other carbon dioxide inside of the spectrometer itself. which isn't that surprising. Actually, somewhat surprisingly, this stray carbon dioxide isn't going to cause us any problems whatsoever. Okay, the next thing that we'll do is to open up the spectrum that we just took of carbon monoxide. Here it is. And so that you can see both of these at the same time. So now we're looking at the reference spectrum, that's in red, and the sample spectrum, that's in green. And you can see that the carbon monoxide features are only present in the sample spectrum, okay? Now the last thing that we're going to do is we're going to take the ratio of the sample spectrum to the reference spectrum, okay? That'll take just a second, but it's not that interesting to see how one makes the software do this. So I'll just skip to the result. 1 second. Okay, we're done. Now the spectrum in red is the ratio, what's called the transmission spectrum, and the spectrum in green is still the sample spectrum. Notice that the background for the transmission spectrum is a flat line because we've divided out all the features that aren't due to the gas in the cell. Here, let's zoom in on the features of interest. And you can see that they both look great, but in the transmission spectrum, the background is very flat and clear, which is going to make analysis easier. Let's get rid of the sample spectrum now. I'll just clear it from the display. There we are, and we're ready to go. Now, the next step would be to convert this from a transmission spectrum, where 100% means full transmission, to an absorbance spectrum. The absorbance is minus the logarithm of the transmission. Let's go ahead and do that. So we'll process this into absorbance. Well, it's a simple transformation, which the machine has no problem calculating. Let me just rescale, and there we are. The main thing is that now the lines go up, and the height of the line is proportional somehow to the concentration of the absorber. So it's easier to analyze. Let's zoom in a little bit more. Okay? Very good. Now, the last thing that we'd like to do before you can start really analyzing the data is we'd like to know the location and the strength of each of these lines. Now, we can measure them separately, one by one with a cursor, but that would be very time-consuming. Luckily, there's a routine built into this program called Find Peaks, and we'll use that now. This has a peak finder, which will look for the sharp features and then label them. There are two controls to the peak finder. One is a threshold, which looks like this black line here. If I make the threshold lower, then more of the peaks will show up. The second thing is a sensitivity control. Here it is. If I increase the sensitivity, more peaks will get labeled. However, if I make the sensitivity too high, then all the little noise features will get labeled. We don't want that. So we'd like a sensitivity about here. Now we seem to have all of the peaks, or most of it, or all of the strongest peaks. We don't have any noise features. So now we can copy this data to the clipboard, and then we can paste it into an Excel file. If you'll hang on 1 second, Excel will open. Let's just click a point here, and then we can paste. Ah, so easy. All right, that's the data that you'll analyze for carbon monoxide. Let's stop there.